to today's Green Business Fund webinar. Today we're going to look at controls and the application of controls to provide energy savings. So the agenda is split across 4 key areas. So after a brief introduction, I'm going to talk about the opportunity to utilise improved controls on heating, cooling and ventilation systems, also on lighting, for motor control, and also for use on manufacturing systems. I'll then give you more information on the Green Business Fund itself and how to avail of support through the Green Business Fund. So firstly, just to give you a bit of background on the Carbon Trust, we're a not-for-profit organisation with a mission to accelerate the move to a sustainable low-carbon economy. We provide support in 3 main ways. We provide it through advice to businesses, government and the public sector, and through schemes such as the Green Business Fund. We also provide footprinting advice to measure and certify the environmental footprint of organisations, of products and of services. And we also provide technology advice to help develop and deploy low carbon technologies and solutions. So in terms of today's webinar, as I said, we're going to focus on 4 key areas for the use of controls, and we're going to examine how controls can be optimized and commissioned for efficiency. We're going to look at when it's cost effective to change or to install controls, and also to give more information on how the Green Business Fund can be used, firstly to identify opportunities for savings at your site, secondly to find suitable specialists, and thirdly to get the capital contribution towards your project. So in general, controls projects offer some of the quickest returns of investment. Paybacks can often be less than a year, and because the technology applies across large systems for a small investment, they are a very effective way of reducing your energy costs. So in general, when we're talking about controls, we're talking about them in application to a system. So a system left uncontrolled will operate with full output. It'll be potentially operating at its maximum capacity continually. So to improve on that, it's often the case that sensors need to be brought in. For a heating system, that could simply be a thermostat. For a lighting system, that could be daylight sensing to check when there's enough available natural light. But that sensor can then feed back into a controller, which can adjust the output of the system. So once there's that sensor feedback into the system has an option then as to what to do next. It can either switch off entirely, it may not be needed at all, which will have obvious energy savings. It could perhaps reduce output, and again that will improve on the energy performance. Or it may be the case that full output is required and it can continue operating as it was previously. So it's really that principle that comes through in all of the technology areas that we'll look at today, and the opportunity to deploy that applies across a range of technologies and a range of systems. So the first area that we'll look at today is the efficient control of heating, cooling and ventilation systems. It's an obvious application of controls, and one of the key areas to focus on is temperature. Obviously there's a need to maintain a comfortable temperature, but you want to avoid overheating or overcooling. As you can see here in the chart, we would recommend the use of a dead band. So we'd recommend that your heating system heats until the building temperature is around 19 degrees Celsius, and we'd recommend that the cooling system cools until the until the temperature is down to around 24 degrees. And that area in the middle, really, that is essentially a dead band. So you should neither be heating nor cooling across that temperature range. So there's a 5-degree dead band there where your heating system is off, your cooling system is off, and your building is at a comfortable temperature. So much of that can be achieved through room sensors and thermostats across relevant parts of the building to control your heating system and to control your air conditioning system. Other sensors will be important in terms of boiler or cylinder thermostats. Also, the use of thermostatic radiator valves can be beneficial, just to allow manual control on individual rooms and to have them turned down to minimize the heat requirement in certain areas. And in addition, you can utilize external temperature sensors to compensate your system for external conditions. So that might mean that your heating system comes on earlier on particularly cold days, or if it's warming up outside, it gets the chance to switch off early as well. So it's very basic stuff, but there's significant opportunities for savings from temperature control. So if you lower your heating temperatures by just 1 degree Celsius, you can save in around 8% on your fuel consumption. And that same principle will apply to cooling. If you increase your cooling set points so you're not cooling down to as low a temperature, again, you'll see similar levels of savings on the cooling systems. Another important factor is controls, is time controls. So there's no point heating or cooling a space if it's unoccupied. So for a business with basic needs, you may operate fixed hours, 9 to 5, Monday to Friday. So ensuring that you have good time controls, that the building is warm enough at the start of the working day and that the heating is switched off at the end of the day, may well provide the level of control needed for your business. There's a variety of types of time controls. You'll still see older 24-hour dials or 7-day timers with pins in them, which may be fiddly and complicated to use, but can be effective if programmed correctly. More commonly nowadays, you'll see the modern electronic time switches as pictured here on the slide, and that gives the functionality to maybe set in quite a few time and indeed temperature settings throughout the day. So the main need for control is really to link your heating, your ventilation, or your air conditioning system with occupancy. And in advanced systems, you may use the likes of presence detection or indeed CO2 sensing, which we'll come on to provide feedback on the occupancy of the space, and that'll allow you to adjust the ventilation or the heating and cooling requirements. And indeed, as I mentioned just there, airflow is important as well. So in larger buildings, you'll often see centralized air handling units, which can provide heating and cooling to a space through the ventilation system. So it'll often be supplying air and extracting air to the space, and avoiding excessive airflow in those circumstances can minimize your heating and your cooling loads. So timer control again will be important there, but in addition to that, the use of CO2 sensors in particular can help modulate the airflow based on the air quality. So typically in fresh outdoor air, you'll see CO2 levels of maybe 400 parts per million. Indoors in a comfortable space, that might be 700 parts per million, but as that increases, it'll become increasingly stuffy. The risk though from an energy perspective is that you overly ventilate and you're providing airflow beyond what is required, and by close control of that using CO2 sensing, you can get a balance and optimize your system for energy performance. And indeed, it may be the case that if you have fixed speed systems, the use of variable speed inverter drives can enable that. So we'll come on to that in the motor section. And there's more information on the Motors and Drives webinar as well, which goes into motor and drive use in more detail. And it's often the case that the systems can be complex and might need management by a building energy management system or a BEM system that will be taking charge of multiple sensors, multiple thermostats, and multiple controls across a building. So it's worth looking in more detail if you do have a complex system at your BEMS arrangement, or if you have a complex building that doesn't have a building energy management system. It may be worthwhile to investigate the possibility of installing one of those to improve your sensor control and to improve your system operation. So it would typically be appropriate for companies with a high level of expenditure on HVAC, on heating, ventilation, and air conditioning. And again, we have a separate webinar specifically on HVAC, which goes into this in more detail. So I'll just conclude this section with a case study. You can see here this is an example of use of controls by Sovereign Group. They installed heating controls to provide an optimized stop program. So that they are a manufacturer of windows and doors based in Lancashire, and essentially installing this web-enabled system allowed them to gradually reduce the ambient temperature just in the last hour of the working day. And because they were a significant operation, that provided big savings. They spent about £18,500 on the system, but they were able to realise savings of close to £5,000. And again, that was just over that last hour of the day. We were able to give them a capital contribution, 15% of the value of £2,700. So their payback before consideration of the contribution was 3.8 years, and after was just 2.8 years. And again, it's worth emphasising that control system was just looking at 1 hour of the working day. So for systems that are improving energy performance across a wider time period, they'll see savings beyond that. Move on now just into the to the next section, which looks at the energy efficient control of lighting systems. So again, we've looked at this in the lighting webinar, but it's often the case that you can see significant savings by changing your light source. So going from conventional fluorescent or metal halide or indeed incandescent technology to LED will provide good savings. Typically 70–80% is possible in doing that. So you'll get good savings from changing your lighting, but it's always worth looking at bringing in controls both at that point and even after you've installed LED light sources. It can be beneficial to bring in forms of control such as presence detection, which will sense whether there's anybody in the space and switch off lighting when it's not required, and also the use of daylight dimming. So in many buildings, you'll get good available light through roof lights or through windows through much of the day. And by integrating your lighting system with daylight sensors, they can switch off or dim when sufficient natural light is present. So for lighting projects, whenever you're coupling changes to LED with controls measures, you can see savings of 70–80% plus, and that controls measure will just enhance your savings further whenever it comes to lighting projects. And again, specifically on lighting, we have a webinar available on that topic, which gives more information on LED lighting in particular. So in terms of options, we've mentioned a few there already on lighting. Presence detection is widely used through the use of PIRs to detect motion and to switch off lighting unless somebody is in a space. Daylight dimming sensing too is useful, as too is simple time controls. Again, back to the similar example as we had in the heating section. You can set your lighting to switch off basically at the end of the working day, or after cleaners have gone home, or at that stage, and do that automatically to make sure that the lighting isn't left on. That can also be achieved using a last person out switch. So having all the lighting systems in the building set up to be switched off with one switch is an easy way to switch off all the lighting at once, rather than have somebody walk around the entirety of the building to switch off individual lighting circuits. And indeed, for external lighting, the use of photocell control will pick up on the level of daylight and switch off lighting when it's not required at night, and that obviously will track the seasonal change in daylight as well. So looking here at presence detection, this can be integral to the luminaires themselves. So you quite often will see this built into panels, built into lighting systems directly. So individual lights can switch off or dim as required based on presence detection, or often you'll get passive infrared sensors, as we see on the right, controlling a room or an area of a building. Ultrasonic sensors can be used too. These emit and receive high frequency sound waves and trigger a pattern for a response. They're more sensitive, but they can cover a larger area. Typically, though, they are slightly more expensive. They can be well used in larger spaces, as too can microwave sensors, which can give good coverage for large spaces such as warehouses. And as well as looking at these sensor controls, overrides are beneficial too, such as the last person out switch that we mentioned, which can switch off the system and avoid it being triggered unnecessarily when the building's unoccupied. They wouldn't apply to all areas, and consideration needs to be given to the likes of production spaces or catering spaces, or areas, you know, where a switch off in the lighting would cause difficulties. If somebody's operating a machine, or if they're cooking or things of that nature, you want to make sure that the lighting's kept on continually in those areas. Daylight control, as we mentioned earlier, will be beneficial. You can see here, this is an example in the image of a shopping mall. It has good daylight control. All the lighting is switched off. You can see here, hopefully on your screen, that there's areas of lighting right down the middle of the mall there that's all switched off, and much is switched off at the side. And at the same time, there's adequate natural light for everybody to walk around in the space. If that changes, if it gets dark at night, or if it clouds over particularly, then the lighting can come on, and it can either ramp up or switch on to full brightness. And using daylight control coupled with LED technology is very effective due to its dimming capabilities and its ability to adjust its brightness over a wide range. And then simple methods, if you have light switches in place, it's useful to make sure that they're well labeled, that everybody's aware of what the lighting switches will do, which areas they'll switch off. You can see here in the right, you wouldn't be quite sure of what was going to switch off with the wide array of switches there. But if you have good labeling and good information and good discipline in switching off, that can be very effective, as well as the more advanced automated systems. In addition, the use of scene setting can be beneficial in hospitality environments, so adjusting the level of light throughout the day, having different levels perhaps at breakfast time and in the evenings, depending on what's required for the mood of the building. That can be beneficial both for the atmosphere, but can also be optimized for energy performance. And looking here just at an example on the investment case for controls. This first example here is the investment in LED lighting. So this is a replacement project where the existing lighting is being replaced, and essentially I think the project value here was in around £50,000. So that's enabled a big saving in lighting energy use to start off with. Payback period without controls is 5 years, but if you're to bring in controls, that can improve dramatically. So the level of saving can be increased, and the payback can be improved. So you can see here the energy savings increasing as the controls savings increase. So as we reduce the amount of lighting operation by 10%, 20%, 30%, the level of savings increase and the payback decreases. So it can improve the payback period for a lighting replacement project, but as well as that, sorry, just some technical difficulties. Yes, so sorry, as well as that, it can be very effective when used on its own. So in this example, we're looking at a case where maybe somebody has invested in LED lighting, they've reduced their lighting capacity to 16 kilowatts. Now it'll be operating much more efficiently than the levels we saw on the previous slide for the old technology. But at the same time, it can be improved further. So if you were to spend perhaps an additional £2,500, in this case, it could enable further savings. And depending on the level of potential, you'll see a very quick return on investment for that. Obviously, if there's only a slight benefit, maybe a 10% saving on lighting, you might see a payback of in around 5 years in this example. But as that increases, as that potential increases through 10, 20, 30, 40%, you're going to see much improved paybacks just for that controls measure. So it may be the case that you've upgraded to LED lighting recently. You maybe haven't taken the opportunity to bring in controls, but it's not too late to relook at that, to maybe consider bringing in additional daylight or occupancy controls to reduce the operation of the system and provide increased savings. And in the case study here, we can see an investment by Blackout Limited. Blackout are a theatre and an event company. They're one of the largest suppliers of theatrical drapes. They were able to install new LED lighting in 2 of their warehouses. And as well as installing the lighting system, they were able to use PIR controls to reduce the operation, which is particularly beneficial in a warehouse space that may not be continually occupied. So you can see here their project cost was in around £47,000, At that time, they were able to get a capital contribution of £6,800. That's now capped at £5,000. But in any case, they were able to see good savings of £9,000, and the project payback was 4.5 years, even without the contribution there. So you can see it's worth bringing controls in, and that would have provided a good proportion of the 76% lighting savings that they were able to achieve there. Okay, so the next section we're going to go on to here is the efficient control of motors. So for motors, they're often not operating in isolation. They're often part of a wider system or part of a machine, as you can see here in the image. So there'll be multiple motors in a system like that, all controlled in a variety of ways. So it's important just to consider the overall system requirements as well as the motor requirements. The majority of motors that you'll see in industry would tend to be fixed speed induction motors. And by fixed speed, what we mean there really is that they're providing a constant output that will be based on the frequency input. So the main supply will typically be giving 50 hertz as its frequency, and that'll dictate the output speed of the motor. The motor then will be linked to transmission systems. It'll often use belts or chain drives to link to other systems, and that'll change the speed. But again, if it's a fixed speed motor, that'll ultimately just be a fixed speed output that is being given out there to the system that's involved. So in simple terms, the more speed that's required, the more power that's needed. So if you can reduce the speed of your motor, that will reduce the power requirement. And that speed reduction can make significant energy savings, especially whenever it's applied to fans, to pumps, and to compressors. And the amount of saving that's available is dependent on the reduction that's possible through the speed and power relationship that we'll come on to shortly. And indeed, as mentioned earlier, the speed power relationship is different for different types of load. So essentially, where you have a constant power, there won't be an energy saving to be had in that case. That's the red line along the bottom there. Where you have a constant torque arrangement, essentially that'll be proportional to the saving will be proportional to the change in speed. But where the change in speed really comes into its own is on the application to variable torque loads. And you can see here the nature of the graph means that even small reductions in speed lead to large energy savings. So you can see in this example, considering what it'd be like to drive your motor the same way you drive your car. So a fixed speed engine with brakes to control the road speed. So that, as ridiculous as that looks, that is what can happen in some systems, that you have fixed speed motors that are being damped or being controlled in very basic ways to reduce their speed. But ultimately, what you need is a variable speed drive or an inverter system to control the speed of the motor intelligently. We'll probably use the term variable speed drive and inverter interchangeably here, and essentially they are the same thing. So looking at variable speed drives in more detail, we have an example here on the left of a pump system. And you can see here the profile of energy use relative to a change in flow rate here at the top for a fixed speed motor. There is a slight reduction as the flow rate changes, but it's nothing in comparison to the change that you see through a variable speed motor. You can see there the profile of the energy use changes dramatically as we come down the curve and as the speed reduces to match the flow rate. So there's significant power savings to be had, as can be seen in the graph there, and that cubic relationship that we saw on the previous chart means that typically what you can see is savings of 50% achieved by reducing fan or pump flow rate by just 20%. So that's where the big savings come in, and it makes a significant difference for variable torque loads if you can apply a variable speed drive. That applies to the pump systems, as we see here, also to fan systems. You can see in the chart on the right that there's the same principle in terms of the level of saving and the profile of the graph. So anything that has a variation in flow rate, you can apply variable speed drives to quite effectively. So just looking at a brief case study here on variable speed drives. We've got an example here of a fixed speed pump operating at the top here for 6,000 hours per year. It has a motor rating of 22 kilowatts, but runs with an absorbed power for its duty of 15 kilowatts. That means that it runs at a constant speed of 1450 RPM, and overall that'll continue at that output across the 6,000 hours, consuming 90,600 kilowatt hours in the year, and that will give a cost of £8,150. If that same system was to be used with an inverter, what you'll see is that for 40% of the time it runs at full output, still at the same 15.1 kilowatts. The speed is the same at 1450 RPM, but what it's able to do for 60% of the time is to run at a much reduced power, to run at a power of 6.4 kilowatts there, and again at a lower speed of 1087 RPM. So that ability for it to sit back at a much lower level of operation for much of the time gives an energy consumption for the year of just under 60,000 kilowatt hours. So a saving there of about 30,000 kilowatt hours, which works out in cost terms to be a saving of about £2,800 a year. So that was achievable for this motor size for an investment of £4,000, and it's often the case that you can install variable speed drives on existing motors. You don't necessarily need to replace them. The inverter or the variable speed drive can be installed with an existing motor to vary the frequency and to vary the speed of the existing motor. In this case, we were able to give a capital contribution of 15% in around £600, and overall that led to a net payback of just 1.2 years, and you can see that's a very attractive return on investment. So a couple more examples here. Compressed air at the top. A manufacturing company replaced a 22 kilowatt fixed speed compressor with a 30 kilowatt variable speed machine. So in this case, they replaced the compressor, competitive cost there of £10,000, and they were able to achieve savings of just over £4,000 a year with a payback of 2.5 years. And again, that can be achieved by speaking to specialists who can look at your air demand and look at how it will modulate with a variable speed compressor. Another example here is the use of inverter controls for fans. A glass manufacturing company equipped two 200 kilowatt motor fans with an inverter. The cost there was £43,000. Large system. Again, they will have retained the motors in that case, but the saving there was close to £36,000 a year, giving a payback of just 1.2 years. Okay, to the last section, and that last section is the use of efficient controls in manufacturing. Um, so basically, looking at the likes of conveyor system, there's no point operating the system when it's not required if there's no packages or things to be conveyed on it. The use of sensors can be deployed to detect that requirement and to switch the system on and off as required. That obviously will avoid energy wastage. So the system will need to run them whenever there's a high volume going through it, but it can sit back at low speed or switch off when it's not required. And controls come into play even more so in high intensity systems. The example we have here is for a paint tunnel oven. You can see here that the level of loss is very high, so there's losses from the open ends as equipment comes through the paint tunnel. There's losses through the walls of the oven. There's losses from the exhaust gases, and also the likes of the conveyor and the rack is being heated as well as the product itself. So in this example, we're indicating that the heat required just to heat that product and to cure the paint is just 7%. So given that intensity, controls are very important. Firstly, we want to make sure that the oven is at the right temperature. We'll also want to make sure that the product isn't in there any longer than it needs to be, that it's moving through at the correct speed to get the paint cured correctly without it being in there for too long. Also, we'll want to maximize the occupancy of the chamber. So if the products are going through on hangers like this and there's empty hangers down the line, it's wasting a lot of the energy use of the oven. So optimizing that and perhaps switching off the oven at an earlier stage will provide good savings. Another example here that we're going to look at a case study on is process control of a dust extract system. So for a joinery works or a business of that nature, they may well be operating a number of different lines, each with the extract ducts taking the dust and the wood material away. That's quite often using centralized fan motors. And it can be the case that that fan simply operates at a fixed speed. So even if the line utilization changes, that fixed speed fan might just continue to operate at the same speed. Using a variable speed fan motor, using damper control to switch off the lines when they're not required can make a significant difference in the energy performance of the system. And that indeed, that's something that we see here in this case study. It was a joinery company in the Northwest that had two main extract systems. They were making good use of wood waste to heat the factory. However, both of their large 55 kilowatt fans were operating at fixed speed, which is leading to excessive energy use for extract. So they were able to bring in automatic damper control on both of those main motors and also utilize variable speed drives to control the main lines. So that operated across 17 machines in the factory. The cost that was estimated was about £55,000, and we were able to offer a contribution in this case of £5,000. Annual saving 13,200 there, with a project payback of about 4.1 years. But I suppose the key thing in this one really is the level of extract savings. So you could see there that the energy use on the extract system was halved by introducing the variable speed drives and the damper control to minimize the energy use there. Okay, well that concludes the main technology areas. I'm just going to give you more information now on the Green Business Fund itself. So the Green Business Fund is operated by the Carbon Trust to help SMEs to improve sustainability and energy efficiency. It runs across England, Scotland and Wales, and we have funding in place at present that will continue the scheme well through 2018. So we provide a range of advice, training and also direct financial contributions towards capital equipment. So in basic terms, in terms of companies that are eligible for it, firstly, you need to be in England, Scotland or Wales. Secondly, you need to be an SME. There's some other additional organisation types. Schools are eligible, as too are sole traders and charities. And in terms of how we define an SME, you need to meet two of the following criteria. So you need to have no more than 250 employees, or turnover less than 26 million, or a balance sheet not in excess of about 13 million there. So as long as you meet two of the three of those, you'd be classed as an SME. And also you need to ensure that not more than 25% of your business is owned by a non-SME, essentially. But if you have any queries on that, our customer centre would be happy to help you on that. So there's a range of workshops being delivered across the country. These are hosted by the Carbon Trust and help to provide an understanding of measures for reducing your energy expenditure. They're available to companies with less than 50 employees in this case, and we've trained over 135 companies so far. A couple of examples of workshops coming up there. There's one in Skegness on the 14th of March, which will be next week, and also there's one there on the 18th of April in Alton in Hampshire. We also provide opportunity assessments. These are either remote or on-site, depending on your energy expenditure. They're delivered by one of our team of Carbon Trust engineers, and will typically focus on the top three recommendations for your business, just to give you a clear identification of worthwhile opportunities to take forward. Beyond that, we also provide implementation advice that can help link you to our panel of accredited suppliers, and we can also assist in running a tender process and evaluating the proposals that are returned to make sure that you're getting the best value for money in terms of whole life cost. In terms of the accredited suppliers themselves, we have a list of close to 200 on our website. You can search for suppliers on the Green Business Directory, which is accessible from the Carbon Trust website. You can see here in the example on the slide, we have selected controls. So there's a range of controls suppliers across the country. You can check for ones that are in your vicinity, or you can ask for advice on recommendations from ourselves on suitable suppliers. And also, once you've got a project ready to go, we're able to provide financial support towards it. We're able to offer up to 15% of the project value to a maximum of £5,000 towards the project. That applies where projects pay back in 5 years or less. Projects with longer payback periods are still eligible, but we cap the contribution based on 15% of 5 times the annual savings. So thanks very much for listening. I hope that was informative. Thank you.